Hello, and welcome to our fourth and final installment of Let's Play with the Sampling Distribution. We are going to again be doing one for a proportion here in number 4. This is our final one. So we're looking at some data where, according to our most recent data, I don't remember what year this is from, so I hope it's more recent than I think it is. I think it's a couple years old, so recent, not so much. Anyway, 9.5% of all engineers, including electrical, mechanical, industrial, and civil, so not nuclear, were women. So suppose we're going to look at a random sample of 75 engineers that's selected. How likely is it that in a sample of 75, it will only contain 9 or more women in these positions? So 9 or more. So the or more part is telling you, hey, we're going to be looking at a greater than here, and obviously how likely is another way to ask you how often or how probable is it. So I'm going to be setting up a sampling distribution for a proportion here, and the real way I know this is going to be proportion is what I'm doing is counting stuff. 9 of them are women out of 75. So that's a big clue that I'm going to be looking at counting. So the first thing I'm going to do is I'm going to set up my sampling distribution. So I know that my mean of the sampling distribution for a proportion is that 9.5%. So I'm going to move the decimal place twice and put it into a proportion rather than a percentage. So 0.095 is what I'm going to be working with. Cool. And then I need to form my standard deviation of the sampling proportion. Oh, that P looks bad. It looks like an R. That's a B. All right, you know what? I can't live with it. I'm sorry, peoples. Let's redo that one. Why is this green? What was I thinking? Okay, there we go. I'm getting it together. I'm going to be professional. Here we go. So I need 0.095. Oof, rough 5. 1 minus 0.095. If you're wondering why I'm writing all these, also the equation editor from Microsoft Word, if you've ever tried to use it. It's a thing. Cool. So I need to calculate what this is, and that'll give me an idea of the distribution I'm looking at. Ooh, I'm really questioning whether or not this one's going to be normal. So I also should make sure I check to see what 9.5% of 75 is. So remember, it has to be at least 5 for me to be able to do this. So let's do that real quick. 0.095 times 75 needs to be at least 5 for me to do this. Ah, it's 7. Okay, we're good. Cool. Now let's go ahead and calculate our standard deviation of the sampling proportion. So I'm going to do 1 minus 0.095, all right, times 0.095, and divide that by 75, and then take the square root. Okay, so remember, don't round too much here. That's the key. So let's do 4 places like I usually do. Actually, maybe I'll do 5 with this one because that'll be a 9. So I'll do like 8, 6. I should have left more space here. Okay, so I'm all set up now. Now I can calculate some probabilities. I got my mean, got my standard deviation. So I want the probability that my proportion is greater than, because I'm looking at more than 9 out of 75. Oops, I'm going to have to calculate that before I can go any further. Whoopsie daisy. I'm going to run out of space. That's not good. I thought I left enough space. I'm wrong. I need one day where I have to do nothing wrong. It'll be a magical day. I hope you're all there for it. Ooh. That's kind of big compared to, oh, well, I guess it's about a little bit more than 1 standard deviation away. This shouldn't be too unusual. So what I'm doing by trying to judge is this big or small is I'm taking my mean and I'm adding a standard deviation to it to see how close it is. So it's only about 1 away. And that's just a trick to decide if it's unusual or not. But that's not what the question is asking. It's not about unusualness. It's asking us, see if I can select all this and move it down. Nope. That was an adventure in futility. Let's do probability. So I want to calculate graph, probability distribution plot. Oh, view probability. Sorry, I know it doesn't record my screen making noise, but evidently I hit it twice and it didn't like that. So I'm putting in my mean, 0.095. I'm going to put in my standard deviation. Again, I checked earlier to see if this was normal when I did the whole oh, what's 9.5% of 75 thing, because if it wasn't at least 5, we weren't going to be able to do this. All right. So we're going to go over to shaded area, go down to X value, put in my proportions. I want greater than, so I do want a right tail, and greater than 0.12. Yeah. 0.12 seems too big. Really? 9 out of 75 is 0.12. That's 12%. Okay. All right. Let's see how we be. Oh, that's pretty big. Okay. It's not too unusual. That's what I was thinking. It's nice when it matches what you think it's going to be. You know what I'm saying? I don't know if you can tell this, but clearly I did not write this problem. This was written by a friend of mine who also teaches statistics, but at the University of Wisconsin. Her name is Meta, which is I don't know, maybe I'll name one of my kids Meta. I like her name. I think it just sounds cool. Of course, that's the story of everyone's life. You always hate your name. I always thought I could make a good Sydney. Now I'm just talking about nonsense. Anyway, so 23.02%. All right, so that wasn't unusual that much as I thought it was going to be. I thought it was going to be far away. But then again, when I checked the standard deviation, I should have known that. Anyway, so let's try fewer than 5. So similarly, they've given us a count, 5 out of 75. So I'm going to have to change that into a proportion again before I can proceed. But this time I'm on the same distribution, and I already made the mean and standard deviation, so that's good. So P bar, fewer than, so less than 5 out of 75. So I'm going to figure out what that is. And then use Minitab to calculate the probability. So let's grab our little handy dandy head calculator. 5 divided by 75. That's pretty small. This one might be one that, no, it's not going to come up that unusual. It's about 1 standard deviation in the other direction. Let's just use 667. That seems like enough places, right? All right, so since I'm using the same distribution, I'm going to hit the Edit Last Dialog box to bring back up the same stuff. So I'm hoping you notice this feels like we're combining stuff from like earlier chapters with later chapters. It's a nice sort of synthesis moment for all of what we've done. So same mean, same standard deviation. I'm normal from what we checked earlier. Let's go to shaded area. I'm going to want a left tail. Since I'm doing fewer this time, I'm going to put in my rounded value. Now remember, this is only as accurate as your rounding, so if you did like 1 decimal place, you're going to be seriously off. So just be careful with that. Got a little bit of vocal fry going. You hear my voice? It's all cracky. Oh, so it's about the same size, which is not about what I expected. So I looked at 9.5 and I said, oh, well, if I minus 0.3, that's going to take me down to about 6. So I knew it was going to be about 1 standard deviation away, which is similar to the other one. So it's not that different in value. 2006. Just kidding. Anyway, so that's where we're at with that. All right, last question. Now, this is the one I find the most interesting out of all the questions. They ask you, what would happen if instead you use 300 engineers instead of 75? So, what's interesting about that is for part B, if there were 300 engineers and only 5 of them were women, yikes, that would be scary. That would be very small, very unusual. But that's not the only thing that would be happening here. So, one thing to notice, and this might not be something that you notice right away, is if you do 300 divided by 75, that's actually 4. And if you notice where 75 goes in your calculations up above, namely in standard deviation, what you're essentially saying is that when I go to calculate the standard deviation of the sampling distribution of the proportion, if my p-value stayed the same, 0.095, oh well, that just, yeah. Can you tell I didn't bring my good pen with me on this trip? I don't know. If you didn't know, I wasn't at home, and that's why it's a big loud fan in the background. It's because I'm in a hotel. Anyway, same values as we had up here, but the denominator is different. It's 4 times 75. Now, that's why I did that calculation earlier. I don't want to put 300 down there because I want to show you something. Okay, do you remember your rules for roots? Let's find out. It's algebra fun time. So one of the things you should know about square roots is that you can split them. So I'm going to split mine in a very weird way. So I'm going to keep my numerator and denominator and stuff and write this very strangely. Ready? 1/4 times 75. And now my terrible numbers again that I had a hard time writing. 0.095 and 0.905. And again, I'm doing this for a reason. I know it looks weird. So just to check yourself, before you wreck yourself, these are equal because if I multiply their denominators together, I get this denominator, which is 300. And if I multiply their numerators together, I get the same thing as this numerator. So I didn't change anything. They are equal. But the reason I want to do this is I want you to see square root of 1/4 times square root of that stuff. I've read it out loud enough. I don't need to say it again. My 9s are getting better. So it's time for my 5s to decide that they suck again. Yink. Aha. So, non-trick question. What's the square root of 1/4? It's a half. If you don't believe that, what you can do is square root the numerator. Square root of 1 is 1. Square root the denominator. Square root of 4 is 2. So, hopefully, you notice the method to my madness here. If not, take a moment to look at what I'm writing and recognize that it's the exact same stuff I had in part A. I said instead of A. No. Okay, so it's the exact same stuff as part A. Why is that important? So this ends up being a half. So if you do 4 times as many in your sample, your standard deviation gets halved. So if you want to be more accurate, and we talked about this in the lesson, you get a larger sample. How much larger do you need just to improve your standard deviation by half? Ugh, 4 times as much. Thanks, square root. And just to, in case you didn't follow how I know this is the original, if you look at this formula right here, it matches this guy up here. So it's back to the original one I had in part A. Yeah, they be the same. Kind of cool, huh? So how is the things going to change? Well, all of my distances get halved, which means if you look at the distribution itself back in Minitab, where things are at, this is not going to be so wide. It's going to be tighter because my distances get shorter. So where it would fall with the 68, 95, 99.7 rule, aka the empirical rule, would be tighter together, which means values like this would seem farther away because how I judge my distance is half of what it was before, which means when I look at this value, it would be twice as far away. The same thing for the one in part A. It would be twice as far away from the mean because my distance would be halved. Does that make sense? If not, convince yourself of that. If you do the z-score on this distribution, you'll end up with twice the z-score on this distribution. Interesting, yeah? Maybe. Maybe you don't want to think this hard. I don't know. Hopefully you live a good life, though, even if you're not going to think hard.